All right, so tonight what we're going to do is rather than start something new, what we're going to do is get some practice with integration by parts because it is a fairly complicated technique. And it's not as straightforward as use substitution, that's for sure. So we're just going to go through a bunch of examples so that you'll get some real expertise with this before we move into what's next, which is trig integrals. All right, so let me get the document open. So instead of having slides, I'm just going to write the answers of the problems right here. And so why don't we start by reminding ourselves how this works. And we did derive it last time, but let me just show you the final result. And you might recall that u is simply shorthand for f of x. V is shorthand for g of x. Okay, so now before we do that, I want to mention a few derivatives and integrals that will come in very helpful in what we're about to do. The derivative of sine x with respect to x is the cosine of x. The derivative of the cosine of x with respect to x equals the sine of x. The integral of sine x dx, as you can probably guess. Oh, oops, sorry, I missed the most important thing. There's a negative here. All right, that's better. All right, yes, the derivative of sine x is cosine x. The derivative of cosine x is equal to minus the sine x. So the integral of sine x dx is minus cosine x plus c. And then the integral of the cosine of x is the sine of x plus c. All right, I put these here because we're going to need them quite frequently, as a matter of fact. Now, also, I want to point out that if you notice the way this integration by parts formula is written, first we have to identify what we would think of as u and what would we think of as dv. Now, when we look at this the right-hand side, we have u times v minus the integral of v to u. That means we have to do another integral. Now, this one might be solved with u substitution, or it might require us to apply integration by parts a second time. It's possible. So one thing we have to watch out for is that when we choose our u and dv, we have to make sure that we're not creating an even messier integral. In other words, the whole point of all this is to simplify the problem so that it becomes manageable. All right, anyway, let's start with the first one. And this one already involves a trig function. So that's why you see all these formulas over here. Now, it's, you can try either u as x or u as cosine x. It's hard to, u substitution is a little bit easier to describe a strategy for it. Typically with u substitution, what we're aiming for is to choose probably the most complicated part of our expression for u, and then see what happens with du. Here, it's not quite as simple as that. So let us start with, let's say, u equals x, which implies that dv must be cosine x dx. Okay, now, of course, that means that du is just dx. V is, of course, then the integral of cosine x dx. Luckily, we have it in our chart here. Now, I mentioned last time that when we're writing out these definitions, we don't have to worry about the constant, because we will probably end up using multiple constants of integration in the same problem, and eventually they will all be consolidated anyway. So in other words, notice how I just wrote this as sine x without the c. We can save that for last. In other words, when we're done with all the actual calculations, we can then add our c at the end. Now, if this was, of course, if this was a definite integral, we wouldn't have to worry about that. So let's see if we fill in the results. Let's see what we get. So this is clearly u dv. This is our u, this is our dv. Now we then have UV, which means, oh, wait a minute, hold on. X cosine X dx. Oh, sorry. No. This doesn't go here. I'm copying the wrong thing. Hold on. I'll move it over here so it's clear. U is X. V is sine X. Now, in this integral, we have V, which is sine X, du, which is simply dx. Okay. And luckily for us, this is a very simple result. And you can see from up here that is negative the cosine of X. Now we can put the C in. We just have to watch out because remember, we're subtracting this and the integral of sine X is negative cosine X. So the final answer here is actually X sine X plus cosine X plus C. Okay, now what you could do here is if you really want to double check your results, remember we started out with X cosine X dx. You could use, you could just take the derivative of our result and see if it matches up with the original integral. So now this term X sine X will require the product rule. Okay, so I'll tell you, let's break it up into three pieces. All right, now this first one, of course, requires us to use the product rule, which of course, if you recall, if h of x is f of x times g of x, then h prime of x can be written as the following. So if we're looking at just x dx, x sine x rather, and we think of this as our f of x, this is our g of x, then the derivative will be x, and then the derivative of sine x is cosine x. Plus 10x times 1. All right, so the x is f of x. This is g prime of x. The sine is g of x. And this is f prime of x. So we can just write it more simply as x cosine x plus sine x. So that's the derivative of this first term. Now, the second one is easy because it's just the derivative of cosine x. And recall that from the chart, the derivative of the cosine of x is the negative sine of x. And then finally, we also can see very clearly that the derivative of the constant is just 0. So what that means then is that this expression could be written as, okay, the first term, remember, it was x cosine x plus sine x. And then we had the derivative of cosine is negative sine x. Oh, plus 0, not c 0. And so finally, we end up with x cosine x. So if that's the integral we started out with, then we are in good shape. And yes, that the original problem was x cosine x, the integral of x cosine x dx. So we not only found the integral, but we proved that it is correct by taking the derivative of our result. Now, we don't have to do that every time, but it's good to know that we can if it's necessary. All right, so let's try another one. Now, this one involves e to the x. All right. Okay, here we go. Oh, and because of that, let's just quickly remind ourselves. So in other words, the derivative of just e to the x by itself is e to the x, but the derivative of e raised to the g of x, based on the chain rule, which we saw the other day, is equal to e to the gx times g prime of x. Okay. So okay, great. So now this question is the integral of x squared e to the 3x dx. Now, whenever you see a product of two fairly messy expressions like this, there's a very high probability that we're going to use integration by parts. U substitution wouldn't work here because we don't have what we need. So what do we do instead? Okay, well, now remember, let's just rewrite integration by parts. Integral of u dv equals uv minus integral of v du. All right, now, again, you can see there's several possibilities for u and dv. And sometimes you don't get lucky. You know, it's like the good thing about this is if you guess wrong, you'll notice it right away because your result will be even messier than what you started out with. And that just means you've done something wrong. Go back and try something else. So why don't we do this? Let's have u be the x squared. And then dv is the e to the 3x dx. All right, then. So then du is 2x dx. And v. Now, what do we do with this one? What we're going to do is apply u substitution. It's simple enough. It's not, we can't integrate it directly, but we can apply u substitution. How would we do that? Let u be e to the 3x. Oh, I'm sorry, no, it's not. It's just 3x. Then du is 3x, 3 dx, because du dx would just be 3. And that implies that du is 3 dx. So how does that help us? Because now we have e to the u. Now, the problem here is that we don't have this 3. So I'll tell you what, before we start writing it out as eu, let's rewrite this. Now, you notice what I'm doing when I'm supplying the 3, multiplying by 3, which means I have to multiply the outside by 1/3. Now we can go ahead and rewrite this as e to the u du. Now don't confuse, by the way, don't get these two u's confused with each other. This u applies just to this integral. So the bottom line here is that v equals 1/3 e to the 3x. Okay, so in other words, to do the integration by parts, we need all of these. There's u, du, dv, and v. All right. So u is x squared. V is 1/3 e to the 3x. V is 1/3 e to the 3x. And du, way up here, is 2x dx. All right. So as you'll probably discover, as you do enough of these, the first term is not a problem. It's the second term that's always going to give us potentially at least a lot of trouble. So here we have two constants. I guess we can just get rid of them. I mean, move them outside. We're not getting rid of them. So if you want to apply integration u substitution here, what we can do is this. If u is 3x, du is 3 dx. But we don't have 3, do we? So here's what we're going to do. Why don't we rewrite this as minus 2/3? And then what I'm going to do is this. Multiply by 1/3. Now inside the integral, I have e to the 3x, and now I've got 3 dx. So I've got negative 2/9 e to the u du. Okay, now and then remember, for the integration by parts, the u substitution rather, we chose u to be equal to 3x. So in other words, what we just did was we solved for this term here. It is equal to minus 2/9 e to the 3x. Now this term up here is fine the way it is. And then we just need the constant. Oh my God. What a mess. Okay. So if you notice, so what's going to typically happen here is that even if you made the correct substitution for u and dv, that integral that you're subtracting over here, minus v du, will require some technique, which might be integration by parts again, or it might be u substitution, or it could be something else. It could, for example, be integration, trig integration, which we haven't gotten to yet. So you can see why this method is potentially very, very messy, but it does the job. Okay. And that's all we can ask. All right, now what should we do next? No, wait a minute. Let's try this one. Now, this one superficially looks super easy, and it kind of is. Okay. But, and by the way, there probably is a mention of this in the book's uh, appendix. In fact, let me go get that book open. I didn't think of it until just now. It may just be listed there, but I'm just curious to see if they included that one. All right. I think the old computer is getting a little towards the end of its life. We'll see how that goes. All right, so I'm just going to go quickly to the table of contents. There's a trig integrals. We'll be doing that very soon. See, they've got, interestingly enough, I'll tell you what, let's write this in here and see if it works for us. In other words, if it turns out the same. Okay. So according to this, log u du, the integral is u log u minus u plus c. So I'll tell you what, let's do this in two different ways. Let's follow this rule. Now that implies that u is x, all right? If you're going to use this approach, u is x, then du is just simply dx, which means we do have ln u du. Okay. Now, what other option do we have? Why don't we see if we can reproduce this result with integration by parts? So even though we have a formula, it would be good practice to confirm this and make sure we're doing this correctly. All right, so how would that work? All right, let's try. So let's try, how about u? Let's try u equals x. Oh, yeah, dv. See, now there's the thing. This isn't helping, is it? Because then v is just what we started out with. Oh, no wonder. Oh, I know what the problem is. No, no. All right, let's try something different. I just realized. I think that's a better choice. Otherwise, we'll just end up right back where we started from. Yeah, that looks good. Okay, let's try it. All right, so that means we have ln x times df. No, I did something wrong, clearly. I just realized it. Let's try that again. You know what? Yeah, I made the wrong substitution. Let's try that again. Yeah, because it's the dv. It has to be the dx, so v is just x. That's better. Okay, good. Now that's much better. Ln x times x minus the integral of x times 1 over x dx. Now we're getting somewhere. All right. Let's rewrite this as x ln x. Now this is simply the integral of dx. Okay, now we're good. Perfect. Okay, so it just proved that the formula is correct, at least the one we're using. Now, if we had a more complicated case, log x squared, that would change everything. But since it's just log x, we're good. All right. All right, now here's an interesting one. This one involves trig functions. It's good practice, although it's going to take a while. The integral of x sine 2x dx. All right, so how about this? Okay, now, when you have something like this, why don't we go back to our chart? What case are we looking at here? This is the integral of sine u du. And that's just simply equal to negative cosine u plus c. All right, so if that's the case, now you can see there's going to be a bit of a problem here. Not a big problem, but if you let, now again, here we're going to use u substitution. And if we let u equal the 2x, du would be 2 dx, which we don't have, but that's okay. We can supply it very easily. So then when we integrate, so again, we actually don't need the c at the moment. We'll bring that in at the end. So we'll simply write it as minus 1/2 cosine 2x. All right, so we have the four components we need for integration by parts. So u is x, v is this negative 1/2 cosine 2x. V is, again, and du is simply dx. All right, so let's see. Let me write it down here where I've got more room. These cancel. Now this one, the second term, we can solve this with integration u substitution. And so let's just quickly remind ourselves that according to the chart, the integral of cosine u du is positive sine u plus c. So we'll just write it here as sine u. And that means that if we let u be the 2x, du is 2dx. So this expression becomes 1/2. Now, I need a 2dx, which means I need another 1/2 out here. Okay. So we've got 1/4 cosine u du. Okay. All right. Let's see what that turns into. So this is actually 1/4 sine u, but u, remember, was chosen to be 2x. And that's it. Oh boy. Let's see. Oh, here's a fun one. All right, let's see what we can do with this one. X e to the x, e to the minus x dx. So let's try this. How about letting u equal x? Use dx. dv is the e to the minus x dx. Now, this one is almost in the form that we need it. What we're doing here is using u substitution. And we'll let u equal negative x, which means du is negative dx. So that's why I'm writing it like this. And so you're going to wind up with minus e to the minus x. Okay, so again, we have all four components. U, du, dv, and v. So we'll have u, v minus the integral of v. Du is simply dx. So again, this one will be solved with u substitution, where u is negative x, du is negative dx. So I'm going to supply the negative. Okay. Okay. Oh, and of course we still need the C. We do eventually need at the very end, we can plug in that C. Now, something like this would be pretty straightforward to double check. Why don't we give it a shot? Some of the others, well, okay. So that first one is a product. Once again, I'll just quickly remind you how the product rule works for derivatives. So if you've got and you let negative x be f of x, e to the minus x is g of x. Minus 1 would be f prime of x, and minus e to the minus x would be g prime of x. Okay. Oh, let me simplify that just a little and clean it up. So, in other words, you've got negative x times negative e to the minus x plus e to the minus x times negative 1. And then the second term was minus e to the minus x. Oh boy, it looks like I must have goofed it up. There's definitely a sign problem here. You know what? I'll tell you what. Let me do this again. I want to make it a little neater. All right. So in other words, what we're going to do is start by finding the derivative of this piece by itself. Hmm. Uh, oh, I know what the problem. No, no. Okay, we're good. You know what it is? I know what the problem was. So the first term, this is the derivative of the first term. It's the second term that was giving us the problem because the derivative of minus e to the minus x is minus e to the minus x. There we go. Ah, okay. So in other words, yeah, I knew something was wrong. So altogether, you'll have x e to the minus x minus e to the minus x plus e to the minus x. Now we're golden. Okay, because this last two terms drop out, and ultimately you end up with just x e to the minus x, which is the original integral. Okay, very good. All right. God, is there more? Yes. All right, here's another one. Let's try this one on for size. Now this one, no, it doesn't look that bad. Okay. It might at first glance look like nightmare. All right, let's try this. And from way back at the beginning, the integral of cosine x, just x, not a function of x, as you recall, is sine of x. Okay, well, actually, it's starting to look not so painful. Okay, now let's try our formula for integration by parts. So we'll have x squared times sine x minus the integral of sine x. Ooh. Oh no, what do we do now? Well, you know what? It appears, oh, I've been dreading this a lot. We're going to have to use integration by parts a second time. Oh, no, that's just not right. Okay, let's do this. So this one is fine. Okay, we'll leave it. Now, what about this one? What can we do with it? Oh, I know what we'll do. Let's move this 2 out here. That'll make things a little simpler. let's say that we decide. Oh, wait, I copied the wrong. Oh, I don't know. How about u equals x? Okay, so again, we had this way back at the beginning. The integral of sine x dx is negative cosine x. Okay, so we have minus 2. Do we have what we need? Yes. It's not, let me rewrite it slightly. So that it's more clear that this is our u and this is our dv. Okay. So then u is x, dv is sine x. Oh, wait a minute. I got no, I'm looking at the wrong one. This should be u v minus integral v du. All right. So let's see. What does that give us? Now this one is on in our list from the top. Oh, what the hell just happened?